Alrighty, matrix multiplication. This is not scalar multiplication, so we are not just distributing this time. This is a matrix times a matrix, and it's like I said, a little bit more complicated than just distributing. Okay, it's not just distributing. First off, excuse me, I apologize greatly. First off, we have to see if we even can. The certain algorithm we're going to use only lets us multiply matrices of a certain size. Now, it's very similar to what we were talking about with addition and subtraction. However, it's not quite entry by entry. Okay, so we can do a little bit more with matrix multiplication. Basically, what we need to see is, do the insides match? You might be thinking, what the heck are you talking about? The insides? What insides of what? The entries? What are you talking about? So let's take a look at two different sizes. 2 times 2, 2 by 2, and a 4 by 6. Okay? And then we'll also look at actually, let's just look at the ones down here. So let's look at, let's erase that. And let's go look at example number 1. Let's take a look at these sizes. We just need to determine if they can be multiplied. Can they be multiplied? Well, let's take a look at these sizes. What is the size of this first matrix? Remember, we determine a size with rows by columns. So what are the rows times, row by columns of the first matrix? The first matrix has 2 rows. 2 rows, so it's a 2 by how many columns? Just the 1, so it's a 2 by 1, right? What is the size of the second matrix? A 2 rows by 2 columns. Awesome. Now, in order for these to be able to be multiplied, the way we're going to multiply them, the insides of this little equation you see here have to match, meaning this end has to match this end. Does it? Does 1 match 2? No, it does not, right? So this is not able to be multiplied. It does not match. Okay, so we cannot multiply this. Okay, so we cannot multiply this one. But let's check out this one. Here I've got a 2 by 1 and a 3 by 1. What do you think? Do they match? No, they do not, right? So these two do not match, so we cannot multiply. Oops. Let's take a look at one that actually can multiply, right? So let's do a little problem over here. We'll call it, I don't know, we'll do this one, a 2 by 2 of 1, 1, 1, 1 times a 2 by 3. 1, 2, 3, 1, 2, 3. So I have a 2 by 2 times a 2 by 3, right? Do these insides match? They do, right? These insides do match. This 2 on the end matches this 2 on the beginning, right? So it's got to be the insides. It can't just, not the stuff in the front, not the stuff in the back, but the insides. The insides match. And so we can multiply this. And when we multiply this, we end up with an answer of the outsides, but we'll review that again in a sec. We just have to make sure right now that these guys match. All right. Let's try multiplying this guy now. So we're actually going to multiply this matrix times this matrix if we can. But first, let's figure out if we actually can. So what sizes do I have here? I have a 2 by 2. And how many rows? 2 by 1, 2, 3, 4, right? So I have a 2 by 2 and a 2 by 4. What do you think? Can I multiply? Yes, I can. The middles match. And so I can multiply. So we can say, check, can multiply. What we end up with is what's on the outside. And I kind of like to think of this as the accordion rule. If your middles match, you can squish them together. They squish together and they go away. And you end up getting what's left on the outside. You end up what's getting left on the outside. So in this case, when I multiply those two on the inside, they squish together like an accordion, and then what's on the outside comes in. And I end up with a 2 by 4. So when I finish multiplying this, you're going to see in a sec that it does in fact end up being a 2 by 4, but that's what the sizes tell me I'm going to end up with. A 2 by 2 times a 2 by 4 becomes a 2 by 4. So I can go ahead and draw a 2 by 4 over here. because that's where I'm going to put my final answer. Alrighty. Now let's actually talk about how we're going to multiply these. Now the reason we need to check these sizes is because it's a very specific algorithm. Like I said before, everything with matrices is always row by column, row by column, row by column. When you're dealing with sizes, it's row by column. When you're dealing with multiplying, it's row by column. So what we're going to do here is we're going to multiply this row, this red row here, and I'm not going to draw it that way, this red row here, by this first column here. That's what we're going to do. We're going to multiply it entry by entry in this row by column. So what I'm going to do is multiply the first entries in each. So down here we'll do 1, times 1. That was the first entry here and the first entry there. And then I'm going to do the second entries. Negative 3 times 3. Negative 3 times 3. So first entry, second entry of the first row times the first column. And then I'm going to add those two things together. Alright, and when I do that, I get 1 times 1 plus negative 3 times 3 is negative 9, or negative 8. Now negative 8 is going to be exactly what I just multiplied. So if I multiplied the first row by the first column, that is going to end up in the first row, first column. See how that happened? So first row times the first column gives me my first row, first column. Let's try that for the second row. So we're going to do this, or actually let's do the rest of the columns. So now we're going to multiply that same row, but we're going to go by this column this time. So this column. So 1 times, let's see, what was the first entry of the second column? 0. 1 times 0. Plus, now I'll do the second entries, negative 3, and 1. Negative 3 and 1. And let's actually compute that out now. 1 times 0 is 0, plus negative 3 times 1 is negative 3. Those added together gives me a negative 3. So let's see, I just did the first row times the second column. So I'll go to the first row, second column. It looks like negative 3 is my next entry. Alright, now it's getting a little bit messy over here. So I'm just going to go ahead and erase the pink and blue and stuff, just so we can see a little bit more. But that's essentially what we're going to do with every single entry. We're going to multiply the row by each one of the columns. So let's keep going. Okay. I'll do this one in green this time. So I'm going to multiply the first row by the third column. So first row by the third column. 1 times negative 1 is our first entries. Plus negative 3 times 4 is our second entries. And I get negative 1 minus 12 is negative 13. So my first row times my third column gave me my first row, third column entry, negative 13. We'll do it one more time for the first row. First row by fourth column. 1 times 2 plus negative 3 times 1. 1 times 2 plus negative 3 times 1. In other words, 1 times 2 plus negative 3 times 1. And that ends up being 2 minus 3 is negative 1. Alright, and we have our first row. So now we're going to do the exact same thing with the second row. The exact same thing as we did the first row. And again, just kind of clean this up a little bit so we can see a little bit more. And we're going to do the same thing with the second column. We're out of colors. So my second row times the first column, right? So second row, first column is going to be 7 times 1. Those are the first entries. And the second entry is 2 times 3. Plus 2 times 3. 7 times 1 is 7. Plus 6 is going to be 13. So my second row times my first column gave me 13. So in my second row, first column, I'm going to write 13. Alright, let's do the same thing with the other 4. So now I've got second row times second column. 7 times 0 plus 2 times 4 is going to give me 8. 8 was the answer to my second row times my second column. So my second row, second column is going to be 8. And then we'll go to second row, third column, pardon me. 7 times -1 plus 2 times 4 is -7 plus 8, or 1, is going to give me my next entry. And then finally, last but not least, my second row, fourth column is going to give me 7 times 2 plus 2 times -1, which is 14 minus 2, or 12. And I now have my new solution of my 2x2 matrix. Alrighty, so each row by each column gives us a 2x2 matrix. If you have any questions, you can stop the video now. I also would like you to stop so that you could try out this next problem on your own. Yes, I know there are quite a few more entries. It doesn't matter. It's the same process. Row by column, row by column, row by column. So give it a pause and give it a try. Alright, here we go. So I'm going to do this. I'm not going to write out every single equation like we did in the last problem. So in the last problem I wrote all these out. I'm just going to kind of draw the lines, okay? So first I'm going to test that I can even multiply, right? Because that may not be the case. I may not be able to do this. The algorithm might not work, right, if they're not the right sizes. So I've got 3 by 3 times a 3 by 3, right? 3 rows, 3 columns in both. Looks like the insides match, so they accordion down, and I end up with a 3 by 3. So it looks like I can, which is good. Alright, so 3 by 3 is what I'm going to end up multiplying by. This, and I'm going to go row by column every single time. So this first row times this first column, it's going to be -1 times 2 plus 2 times 0 plus 3 times 0. Well, that's easy. It's a lot of zeros. It just gives me a -2. Alright, now I'll go ahead and do the first row by second column. First row by second column. 1 plus 4 plus 0, right? So -1 times -1 is 1. 2 times 2 is 4. 0 times 0 is 0. So I'll add those together. I end up with a 5. Now I'll do my first row, third column. First row, third column. -2 is my first entry times my first entry, plus 2 plus 0 is going to be a 0. Awesome. First row done. Check. Moving on. Second row, and I'm going to clean myself up a little bit just because it's hard to see. Second row, it's going to be second row times first column. 2 times 0 is 0, 3 times 0 is 0, 2 times 6 is 6, or sorry, 2 times 3 is 5. So I end up with a 6. I'm going to extend my matrix just a little bit so that it kind of fits everything in there. Okay, there we go. Alright, second row, so second row, so going second row, second column. 0 times -1, those are the first entries. That gives me a 0. So 0 plus 2 times 3 is 6. Sorry, 3 times 2 is 6. Plus another 0 gives me a 6. Alright. And then my second row times my third column. 0 times 2 is 0. Plus 3 times 1 is 3. Plus 2 times -1 is -2. So that's 3 minus 2, or 1. Alright, second row. Done. Check. Awesome. Moving right along. Can erase that, right? If you like the color system, I highly recommend something that erases. Or you have at least 9 colors, maybe even 12. All right, so the last row, same process, right? This row by the first column, 0 times 2 is 0, 0 times 1 is 0, 4 times 3 is 12, 0 plus 12 gives us 12. Second one, 0, 1, 4 times negative 1, 2, 0. That's 0, 1 times 2 is 2, 4 times 0 is 0, so we get a 2. And then the last one, last row by last column, or third row by third column. 0 times 2 is 0, 1 times 1 is 1, so 0 plus 1. 4 times 1 is, or negative 1 is negative 4. 1 minus 4 would be a negative 3. And we have finally arrived at our 3 by 3 matrix. So sometimes it can take a minute, but it's really the same process over by over. The row by the column, and you add it, multiply it entry by entry. Everything is done entry by entry by entry. All right, pause here if you have any questions about matrix multiplication. All right, the last thing we're going to talk about today is applications of matrix multiplication problems. So this is specifically the multiplication part of matrices, because we've seen a lot of where you could use matrices for linear systems, right? Anything we did in chapter 4.1 can be solved with a matrix as well. So there's a lot of stuff applications there. But for the matrix multiplication specifically, we're going to talk about a few things where it would be modeled with matrix multiplication. So let's talk about that. All right. A contractor builds 3 types of homes, Model A, B, and C, with 2 styles, colonial or ranch. That's not supposed to be ranch, it's supposed to be ranch. Matrix P, right down here, below shows the number of each kind of house that the contractor is planning to build for a 100-home subdivision. Okay? The amount of each of the main materials used depends on the style of house. The amounts shown are in matrix Q below. So here's the Q. So this is our model, how many ranches and colonial we want, and here's what they use for materials. While matrix R gives us the cost in dollars of each kind of material. So matrix R shows us the cost, right? So we've got 3 separate matrices going on here. Concrete is measured here in cubic yards. Lumber is in 1,000 board feet. Bricks are in thousands, and shingles are in 100 square feet. I'm so sorry about all the typos in this problem, but that's okay. So we've got these matrices, right? Question A. What is the total cost for all the house of each model? So the total cost for all of the houses for each model. All right, what we want to do here is we need to first find out oops, sorry, I guess my sound shut off there, sorry. We need to find out P times Q. We need to find out how much material is going to be used first off, right? Because then we can multiply the material by the cost. So let's multiply P by Q. Here we've got P. P is a 2 by 3, right? It's a 2 by 3. I'm so sorry, it's not a 2 by 3, it's a 3 by 2. Right, sorry, rows by columns. You've got 3 rows times 2 columns. And then here in Q, you've got 2 rows by 4 columns, right? So we've got a 3 by 2 and a 2 by 4. The middles match. We're going to end up getting a 3 by 4. So let's go ahead and do that. So we'll get a nice big matrix of a 3 by 4. All right. Let's put the actual matrices themselves over here. So 0, 10, 20, 30, 20, 20. And, oops. 10, 50, 2, 1, 0, 20, and 2, 2. Now, before we move on, Do you think it matters whether we multiplied P by Q or Q by P? Talk about that as a class for a sec. Do you think it matters if I maybe switched those? What do you think would happen if I put Q first instead of P? All right, it does matter a lot, right? Because if we put Q first, Q times P would be 2, it'd be 2 by 4 times a 3 by 2. And do those middles match? We can't multiply that way, right? So it does matter. Matrix multiplication is definitely not commutative. You cannot switch them around. So you have to make sure whichever order you match up in has to be the right order. So we can't go that way. All right, let's go ahead and multiply these. So first row, 0, 30 times first column. So 0 times 10 plus 30 times 50, our first entry is going to be 1,500. First row by second column, 0 times 2 plus 30 times 1, second row is going to be 30. First row by third column, 0 times 0 plus 20 times 30, third one's going to be 600. 0 times 2 plus 30 times 2, the last one's going to be 60. All right. So that was the first row times every single column. We can do the same thing with the second row. 10 times 10 plus 20 times 50 would be our second row. Second row times first column. That's 100 plus 1,000, which would be 1,100. Do the same thing. 10 times 2 is 20, plus 20 would be 40. 10 times 0, so I'm going along this third row now. 10 times 0 plus 20 times 20 would be 400. And last but not least, 10 times 2 is 20, 2 times 2 is 40. Add them together, you get 60. And finally, we'll do the last row. So this last row times this first column would be 20 times 10, which is 200, plus 1,000, that gives us 1,200. And then we take that second row, so third row, second column. 20 times 2 would be 40, plus 20 times 20 is 400. Just kidding, plus 20 times 1, my apologies. Plus 20 times 1 would be 40, plus 20 would be 60. All right, then we've got 20 times 0, which is 0, plus 20 times 20 gives us 400. And last but not least, we have 20 times 2 plus 20 times 2, that's 40 plus 40 is 80. And this will be our P times Q. Remember, P times Q is going to be all the material we need for the house. That's what we need for the house. So now let's multiply that by the cost. Let's take this by the cost. And this cost equation is a 4 row by 1. So can we multiply it by this 3 by 4? Absolutely, as long as we do PQ times R. So let's do PQ times R. Oops. PQ times R. So now we're going to multiply. You know what I'm going to do? I'm going to cut off the tails of this matrix here. I'm going to make it just a little bit smaller because we don't need all that extra space. So now let's take that same matrix and let's multiply it by R. So remember, R was the cost of all of this stuff. So if this is the amount we're going to use, let's multiply it by the R, right? So what we did before is we took the model of every single house and we multiplied it by what each house needed, right? So we multiplied it by the total cost. So this is our total amount. Now each amount is going to cost us something per unit, right? So now in order to find the cost, we're going to multiply by R. So let's go multiply by R. Let's set R up here. This one's kind of a long guy. He's a 4 by 1. And it's 20, 180, 60, 25. So 20, 180, 60, and 25. And you may be sitting there thinking, wow, these matrices don't match at all. There's no way we can multiply these. But look carefully. You've got a 3 by 4 times a 4 by 1. Do the middles match? Yes, they do, right? The middles match. And when we accordion down, we get 3 by 1. So we're going to end up with a 3 by 1. And that totally matches, and it's totally fine. So 3 rows by 1 column. It's going to be a nice tall guy. 3 rows. Ugh, okay, I can't draw today. So 3 rows by 1 column. 1, 2, 3 numbers. Let's see how that works out. It's just going to be kind of a longer thing. So I'm going to multiply this entire brown row by this entire pink column, right? First row, first column. 1,500 times 20 is going to be 30,000. So I'll keep that in mind. Plus the 30 times 180 plus the 600 times the 60 plus the 60 times the 25. I don't know if you could hear it, but I have the clicks of my calculator going. I'm not even mentally computing these. I'm just putting that all in a string into my calculator. I'm letting the calculator figure it out. I definitely could handle it on my own, but I end up with erase a little bit. I end up with my first value being 72900. That's how much it's going to cost me for Model A. 72,000 because it's going to cost me $1,500 times $20 for all of the concrete. It's going to cost me 30 concrete units times 180 for all the lumber. It's going to cost me 600 units of brick times $60 per unit, and $60 of shingle, or 60 units of shingles times $25 a unit. Add those all together, I get 72,900. Let's do the same thing for Model B. So 1,100, so we're going to do the second row times the same column. So 1,100 times that first entry of 20. That's going to give me 22, it's going to give me, it's going to give me 22,000 for the cost of the concrete, right? Plus, let's do the cost of the lumber. 40 units times 180 plus the cost of the brick, 400 units of brick times the $60 each. And then finally the shingles, 60 times 25. Oops. That gives me a total of $54,700 for Model B. That's what it's going to cost to make Model B. Let's do the same thing with the last one. I've got 1,200 units of concrete times the $20. So let's do 1,200 times the $20 plus 60 units of lumber times the 180 per unit plus the 400 units of brick times the $60 per brick unit, plus the 80 units of shingles plus the $25 per shingle, gives me $60,800 for the Model C. So this was Model A, Model B, and Model C. And we can see how a matrix lets us take that information, all those costs, and instead of writing out these huge arithmetic equations, we can keep it nice and confined into a nice little matrix and do everything and just come up with a nice, simple, easy solution. Awesome. All right.